Well, good afternoon. So just to remind you what we were talking about last time, we talked about intelligence, which is the ability to reason and plan, solve problems, complex problems, think abstractly at a high level, comprehend complex ideas, and particularly learn. So we interpret the environment we're in, we learn from it, we adapt to it. So we understand in order to solve problems. That's what intelligence is. And artificial intelligence, or computational intelligence, are programs that then analyze data that represents now the environment, interpret that data and learn from it, learn from these observations inside the data, and then adapt to the changing data or the changing situation. And the AI tools are then tools that exhibit human intelligence. They're not like the humans. They may not reason the way humans reason, but on the outside, the output seems intelligent. Okay? It exhibits intelligence like humans, but they do not process the data and function like humans. That's quite important. And I talked about a test that was suggested by Alan Turing in the 50s to identify whether a machine is intelligent, as intelligent as a human. So you have an interrogator in one room communicating with another human and a machine, and if that interrogator cannot distinguish between the machine and the human, then the machine is intelligent enough to fool the human that it is a human, or it is intelligent. And I mentioned the fact that now the chatterbots that exist that communicate by text with humans, those that are built today, I'm not talking about the 50s, I'm talking about today, they're still not smart enough to fool us to believe that they are humans. They are machines. And they gave some examples. Why? Because the dialogue is not fluent enough. You can see some aberrations in that dialogue. And finally, I also talked about the fact that AI went through ups and downs. The downs were what we call the AI winters. So there were two winters. And each time it went back up because of different circumstances. People realized at one point, oh, it's just utopia, it doesn't work, and then realized, oh, maybe there is a chance, so went up and down. And currently we are on an up for different reasons. One is the fact that computers evolved significantly, so now they have way more resources, they're way faster, they're smaller, and so forth. So many of these programs that were very slow, now they're very fast. And the other reason is that we, rather than focusing on the big AI, we are working on different sub-problems, and people working on these sub-problems made huge advances individually. And put together, actually, it is a huge progress. And I also, well, these are the examples of sub-problems: knowledge representation, reasoning and problem solving, planning, natural language processing, perception like vision, learning, emotion and manipulation like robotics, emotions, so exhibiting emotion and understanding emotion of other people, creativity like painting, poetry, and so forth. So people are working on these sub-problems. And AI achieved quite a bit. And I mentioned the checker program Chinook that was developed here at U of A. And the leader of the group, Jonathan Schaefer, is today the Dean of Science, and he will come to this class to talk about games. Really, the program crushed the champion of the time, Marion Tinsley. There's chess as well. Deep Blue won against Garry Kasparov in '97. There's the Jeopardy Watson program that beat also the best humans. And I'd like to go back to this idea that even though these programs beat humans, it doesn't mean that inside that machine they work like humans. Actually, if you ask Garry Kasparov, why did you do this move in chess, he might not be able to explain why. He knows that's the winning move, that's the best move I can do, but he will not be able to explain why. While the computer will go exhaustively search all the possible moves and evaluate them all and say, this is the best one. And that's not how Garry Kasparov would do. And same thing with Jeopardy. Watson doesn't find the answer like the humans would. But they exhibit, these machines exhibit a human intelligence on the outside. Okay. I also mentioned and Dr. Solez also mentioned the driverless car. These cars made a huge progress, and again, they do not reason like humans do. And we still have a long way to go, but today cars are incredibly advanced. I recently submitted a video on our Facebook website about this car that can park itself. So you drive it to the shopping mall, you leave the car at the entrance of the shopping mall and you go shopping. The car enters the parking and finds a place on its own. And then when you finish shopping, you call it and it comes out. Okay. These cars exist and you can buy them today. It's not a fiction. But again, there's still a long way to go. And as Dr. Solez mentioned, there was an anecdote that Sebastian Thrun told us about when he gave his presentation. They were driving once with this car on the highway, and suddenly they saw this sofa on the highway. The car didn't know what to do. It's an obstacle. So the car slams the brakes, boom, it stops. The human that was sitting at the driver's seat without touching the wheel had to intervene and do an emergency maneuver to avoid that obstacle. But the point that Dr. Solez wanted to insist on is actually a very important point. If you see a mattress on the road, or you see a sofa on the road, as a human, you know that's a mattress, and you know that, well, if I cannot do an evasive maneuver to avoid it, I can hit it, it's okay. Actually, that's the wise thing to do, is to hit the mattress and keep going. But if it's a sofa, if you hit it, well, the damage is huge, can be significant. So you know what a sofa is. You know that a sofa is heavy and hard, and you know that the mattress is soft and has springs and stuff like that. The car doesn't know that. The car is programmed with things that happen normally on the road. This is a complete aberration to have a sofa on the highway. It fell from the back of a truck. So it's not programmed in the car, and the car has to react. So that shows you the difference between a program built in the car to drive perfectly and the program that we build all our lives in our head. It's different. And unless you put all the knowledge of humankind in the car, will it ever use the whole thing? I don't know, it's necessary. But anyways, it gives you an idea about the limitations of some of these programs. Okay, so what we will be talking about today are expert systems and machine learning. So I mentioned expert systems in the 70s, where one of the reasons why we came out of the first winter of AI. And so I'll explain what are these expert systems, and they still exist today, and that will lead us to machine learning. So expert systems are computer programs that try to emulate the human experts. So the human experts have this ability to reason and make decisions based on some knowledge of a problem and knowledge that accumulated in their domain of expertise. And there are expert systems that emulate these experts in different domains, whether it's in medical diagnosis, the first ones were, and actually in medicine, but there are also expert systems in financial analysis, engineering design, like building bridges, manufacturing planning, etc. Why do we need these expert systems, these programs? Well, there are many reasons. One of the most important reasons is that when we have an expert, a human expert in a domain, that human expert is in one place. He or she is not in many places, but we want to replicate that knowledge, that expertise in many places. So that's problem number one. Since we can't clone this human yet, well, we want to take that expertise from the human, put it in the program, and then replicate that program in many places. The other very important reason is the fact that we have these experts that learn during their careers. They accumulate this expertise, and then suddenly they go and retire. Then we lose all that expertise. So how, as a company, how do we keep that expertise? Is by creating these expert systems, so that by the time the person retires, we have an expert system that can replace this person and maybe train others. Okay, so can we preserve the expertise for somebody who's retiring, and can we duplicate that expertise if we want that expertise in many places? Okay. So conventional computer programs, they just follow instructions, very specific instructions what to do. Okay. Experts don't. It depends upon the circumstances. It depends upon the context they're in. Okay, and that's what we want to simulate. So there are two major types of knowledge. I mentioned the experts here. They reason about knowledge to solve a complex problem. So the problem has its own, there's a knowledge around it, but they also have their knowledge that they know about the domain. And so we are talking about expert knowledge. That's the knowledge about the domain that the expert has. And there's contextual knowledge. This is knowledge about the current problem, the facts about the current problem. Okay. So that's what we will have in the expert system. We have then two kinds of knowledge, and then we have some reasoning mechanism to come up with some conclusions. So the architecture of an expert system is as follows. You have an expert, the human expert. With some interviews, we get the knowledge out of this person, and we create what we call the knowledge base. Okay, so these are sets of rules that represent the knowledge that we have about the domain. And then we have a problem here, and from the problem we get these facts. These facts describe basically the current problem. And then we have an inference engine, which is a generic engine that will do inferences on this knowledge and this fact. These facts, actually, it's a collection of facts. And this inference engine is basically using some logic to do, basically here, these rules, you have a premise and a conclusion. It will try to match the facts that we have with the premises of different rules. And then there are some ways of selecting which rule to fire and use that. And then the conclusion of that rule that we selected will become, the conclusion will become one of the facts. Okay. That we add in the fact base here, and then the conjunction of the new fact and the old facts will be used to fire new rules from the knowledge base, and we get new facts. And we continue that process until if we can solve the problem, we'll have a solution for it. Okay, so that's how basically it works. So given the facts, we identify production rules that could fire from the base. We combine some different rules. We have uncertainties attached to the rules. And then we select a rule. Once we select a rule, we add the conclusion of that rule to the facts, and then we repeat, okay, until we find a conclusion. Now, this started in the 60s. The first one was Dendral. It's a rule-based system to do inferences on molecular structure from mass spectral and NMR data. In 75, Mycin was released, and it does some recommendation on antibiotic therapy. So it knew about bacteria and things like that. Dendrol, and the new version of Dendrol actually was the first machine that made some discovery that was published in a journal. So this is the first time a computer made a discovery in 1975. In 79, mycin, they took mycin and they made it generic. We call it the empty mycin. So you can put any knowledge from different domain and it becomes an expert system in that domain. And by 85, the revenue of this field peaked at $1 billion. We're talking about $1 billion in 1985. That's phenomenal. And that's what brought back the AI from the first winter. Okay, so today we have expert systems in medicine, since we are talking about medicine here. There are many different expert systems. They're built in within decision support systems, basically. You don't see them as expert systems per se, but they're part of a decision support system that helps experts make decisions in many fields, as you can see here. So what are the problems with expert systems? It's not as trivial as it may seem. The biggest problem is extracting the knowledge out of the human expert. Often we don't know what we actually know. You ask, what do you know? People give just what comes to mind, but the real knowledge comes out and appears when we are faced with the cases. Okay. Oh yeah, I forgot to tell you indeed this. So it takes a while, and you have to have a very good, you have to have skills, specific skills to create interviews to extract the knowledge out of these experts. The other problem is that when you ask different experts, they may have different opinions. So that creates contradictions in the rules. And if you put both of them in the knowledge base, it can generate problems afterwards. You don't know whether you go left or right. So there are inconsistencies with experts. And regardless of the skills you have to interview the experts, you always miss things. So we have missing rules that we can fill them only when we face the expert with those problems. And by that time, the expert is gone. So we have these missing rules still there. So it's not trivial. It is it can be very problematic. Now there are ways to extract this knowledge automatically, not from the experts, but from the data, and that's what machine learning is doing. Okay, so I'll talk about what is machine learning. Basically, machine learning will do like an expert, but rather than doing it during the whole career, learning from different cases, we'll do it faster, going through all these cases. If we have access to these cases, that's the data, and we'll learn from that data. So machine learning is basically a sub-discipline within AI. It's actually a discipline on its own. It's concerned with designing systems that would allow them to basically change their behavior if the data or the context changes. Okay. So they adapt, basically. They adapt to the environment. Machine learning provides means to learn from large data and interpret the trends in the data. Then you can adapt as the data changes, as opposed to static programs that are written for a specific task. Okay? It's not just a simple set of instructions, do that and that's it. I'll give you examples to really differentiate between programs in normal applications and programs that have machine learning built in. So basically we want to have machines that can learn from the experience and then adapt to the environment as the environment changes. Okay. So here are examples. I'll give you examples of applications that we know of programs that are very sophisticated, but they don't necessarily require any learning. For example, if you take an accounting program, it can be a very complex accounting program to manage a big company. However, as complex as it may seem, all the instructions are already predefined by analysts and programmers, they write every single instruction in the program. How to take money from this account, move it to that account, what happens when you have this, that, this thing, and so forth. Same thing when you have a very large database and you want to extract from that database some records, very specific records. You have to write very sophisticated queries, but there's no learning there. The data is in the database, and you specify what you want, your information need in that query, and there's a program that goes, finds it, and retrieves it. It may look as a daunting task, but again, the instructions are very specific in the program. Another example that may seem very smart, roboting. So robots, like in a manufacturing plant, for building these driverless cars, well, you have an arm that goes in a particular place, puts some pressure, some temperature, does welding, moves objects and things like that. Well, you tell the robot arm which coordinates in space to go to, which pressure to put, and what temperature and so forth. It's all programmed, and it does it again and again, very precisely. Now, you want to change the car. That's the environment. It's changing because I have a new model now. We don't do the old model, we have the new model. Well, you change the X, Y, Z coordinates in space, the temperature and the pressure, and the robot will do it again. Okay? So the robot doesn't learn anything, doesn't adapt to the model of the car that's changing. You give it new coordinates. So here are examples of applications where machine learning plays a huge role. Medical image analysis. So I can write a program, very specific program, that given one image, one specific image, it'll tell me here is cancer, and it'll put a circle around it because I tell it here's the cancer, and it'll draw it perfectly. But if I change the other image, put a new image, it won't know where to put the circle. It'll put the circle in the same X, Y, Z coordinates as the previous image, and that's wrong. So this program is not adapting to the change of images. So a machine learning program, rather than telling it, here's where you put the circle, no, I will show it many images. Each image is different, and for each image I'll say, here's where cancer is. It will learn from that set, then it'll throw it away, it'll just remember what it learned from it. I give it a new image, never seen before, and it will learn, it will tell me where the cancer is. That's machine learning. So in that last image that I showed, I didn't tell the computer where the cancer is. It detected it automatically. So that's machine learning. We use also machine learning for filtering data for analysis. So I show different data. I'll say, this is what I'm interested in, this is what I'm interested in, this is what I'm interested in. And then later I'll present new data, and it'll tell me, oh, that's what you would be interested in. Okay. So an example with robots, since I used robots, dumb robots that do welding in a manufacturing plant. He's a robot like the rover I'm sending to Mars. I've never been to Mars. I don't know how the environment is there. So how would I write a program to tell it, turn here, turn there, turn there? I don't know. Turn this speed and so forth. So what I'll do, I'll write a program that has machine learning, and I'll take that robot and train it on different terrains with that program. The program will learn how to adapt to these different terrains, and then I'll send it with the rover to Mars. Okay. Well, this is not just for NASA. I can have a robot that I'll send in a very hostile environment. For example, I have to defuse a bomb, or there is a fire in a building and I can't send humans because there's too much smoke. I'll send a robot to try to help the humans inside, or extinguish the fire or whatever. That's a new environment. I cannot program that exact environment for this robot. So I will train the robot in different environments, and then I'll release it in this new environment, and it will adapt by itself. Okay. So these are examples. Hopefully they'll give you an idea about the difference between sophisticated programs, but they don't have AI and machine learning, while others that have machine learning, so they adapt to the environment. There are different kinds of machine learning. There is what we call supervised machine learning, where we provide examples, and that's the supervision. We provide examples and the machine learns from that. Where there's what we call unsupervised learning. There's no labeled data that we provide. Semi-supervised, which is a mixture. There's reinforcement learning, where we provide rewards each time the program does something properly, and penalties when it doesn't do it properly, and we tell it to maximize the reward, so it does something, it does things correctly as much as possible. There's also what we call active learning. Anyways, there are many different kinds of learning. I will focus on supervised learning just to illustrate what is this machine learning idea. So supervised learning, basically, you want to create a model that represents the world, the known world, and then use that model that you learned to interpret or label new data, new cases that you haven't seen before. So here's an example that I often use as a metaphor. You have buckets that are labeled. The label on the bucket, unfortunately the color on the projector are not that great, but basically the buckets here have different colors. That's the label of the class. And I have a pile of balls here, and I ask a child sitting next to me and say, watch me, I'm going to put these balls in these different buckets. And at the end, I will ask you to do that task. So watch me and learn. And I don't say anything to the child. Each time I take a ball, I look at it, I may show it to the child, and then I put it in the right bucket. What I choose when I decide to put the ball in the bucket, well, I don't tell it to the child. The child has to observe by himself. But actually what I use is the color of the ball. I don't use the size of the ball, I don't use the weight of the ball, I just look at the color, and if the color matches the color of the bucket, I'll put it in that bucket. Without saying anything, the child just observing will realize that. So at the time I say, okay, now it's your turn, and I give the child the green ball, very likely they will take it and put it in the green bucket. They learned, they created a model, that child created a model in his or her head that says, well, the color of the ball and the color of the bucket should match. Okay. And that's exactly what machine learning would do. Basically, it looks through data. So I provide data. So these squares and their colors, their sizes, and many other features represent, that's the data. We call it labeled data. So the label is actually the color in this case. And I have other data that hasn't been labeled. I don't have the color. And machine learning will go over this data and learn, will extract the different characteristics of the data that will discriminate between the different colors. Those are the labels, the classes, what were represented by the buckets before. And then I will create, the program will create a model. There are different kinds of models, okay? Just consider the model here. We have a cloud, we'll make it more friendly, put a face on it. And that's the model that I will use now with this new unlabeled data that has never seen before, never been seen before. And then I will label the data. Okay. So that's what machine learning is all about. I present some data that I call training data or training set. We create a model, and then we use this model for data that hasn't been seen before to label it. This is what we call supervised learning. So there are many challenges with supervised learning. It's not as trivial as I'm presenting it here. So the first challenge is, what are the relevant features that are important in the task of labeling these objects? The other challenge is what is the best algorithm that I represented here by this green square that passed through the data. There are many different paradigms, different algorithms that are, one is better than the other depending upon the domain I'm dealing with. So it's a very serious challenge. The other challenge is how do I represent this knowledge in terms of rules, a formula, big fancy data structure, how do I represent that knowledge? And then finally, and not finally, well, there are many other challenges, but how do I now effectively use this model that I created such that I can label this data with minimum errors? There are many errors that I'll do, that we call false positives and false negatives and so forth, but I want to minimize that. So I'll give you some examples that you are using today that are using machine learning. You don't know it, but they are using machine learning. One example is spam detection. You all use email. You all experienced spam that is very annoying. Well, there are many programs that have filters to detect spam. And filters are simply rules that are built in the email system. The rules are like, for example, if you have such word in the text or in the subject line, then eliminate this email. Or if the email comes from this list of senders, eliminate this email. These rules are static. And the spammers, they're humans, they're intelligent. They adapt to those rules and they will change. And suddenly you have spam that goes through the filters and you have it in front of you. Those are bad spam filters. The best spam filters will adapt to you. And they will adapt to you differently than somebody else. Because what you consider spam, somebody else may not consider spam, and vice versa. So what these machine learning algorithms will do, they will observe what you like, meaning you open and read, and what you ignore and delete. And will take automatically features from these different classes. So there's spam and non-spam. You'll have two buckets in this case, not many buckets. And will automatically learn what do you like and what you don't like. And the new emails that have never been seen before, it will label them. That's a good one, pass it. That's a bad one, put it in the spam folder. Okay? So that's an example of a program that adapts automatically to the data coming in. Another machine learning application that is used for credit approval. So people working at the bank, they have these applications that will help them say yes or no when you go and ask for a loan. And basically what that program is doing, it went through the history of many other customers, their age, their social status, whether they have a PhD or undergraduate, didn't go to school, or whatever, all different characteristics of the people, and whether they paid back their loan, yes or no. So from all the history, we build a model. Then when you have a new customer, we know their age, we know their status, we know this and that, and the amount that they ask for, and then we enter that in the program, and the program will say, yes, good creditor or bad creditor. And what is the risk? Okay. So that's already built in many systems. Another example that you use and you don't know that it has machine learning are the credit cards applications. When you go and buy something and you scan your card, there is a transaction that is sent to an office somewhere asking for an authorization. Well, during that process, it goes through a model that was built about you already to see whether this transaction fits your behavior or not. So if it doesn't fit your behavior, it will say, no, reject. This is not a transaction that is legitimate. Okay. And this happens in a fraction of a second. The learning happened before. Actually, it continues to, it's retrained again and again because your behavior changes. That is used today. Okay. That's how we can handle millions and millions of transactions a day and make sure that fraudulent transactions are stopped before they happen. Okay. There's also what we call unsupervised learning, as I said. So supervised learning, I have labeled data that I use as training, and I have all these buckets that represent my classes, and I teach the program to put these in the right buckets. The unsupervised learning is when I don't have labeled data for training, so all my balls have no labels. I don't know what labels they have. And in addition, I may not even know, I may know the number of buckets I have, but I don't have their labels. Like here, I have gray, red, blue, and so forth. And in the worst case scenario, I don't even know how many buckets I have. And I have to go through these and find the different groups. Okay. So this is used, for example, in marketing to know the different kinds of customers that exist in my company. So let's go back to the supervised learning, and I'll go through some paradigms very quickly to show you, to give you an idea about the different ways of training a computer to build that model. So basically, we have some labeled data. Some experts already labeled these. And we'll divide this data into two parts. A big part that we call the training data, and a second part that we put aside, that we will use for testing. Then on the training data, we build this model, the classifier. And then how do we know if that model is good or not? We'll test it on the test data. So the test data, the labels are hidden. We know them because we got them from the label data. So we know the labels, but we hide them. And we ask the classifier to predict them, and then we compare what the classifier predicted and what we had. If the accuracy is accepted for the application we're dealing with, then we release the classifier. If they're not acceptable, then we'll train it again with a different algorithm, or we extract different features or whatever, the challenges that I mentioned before. So an example, if I take the problem of spam and non-spam, and I build a classifier, if I make some errors means that I have some spam that I don't delete, I'll present to you, it's annoying. If I have good emails that I considered as spam, it's annoying, but it's not life-threatening. So if I have an accuracy of 99%, I'm fine. 95%, I'm fine. I can live with that. However, if I have a classifier that detects whether I should turn on or off a power plant based on different data coming in, like the pressure, temperature, and all that stuff, I can't afford a 95% accuracy, because if I let the power plant work while I should turn it off, then I may have a Chernobyl. It explodes, and it's very expensive. If it's safe, but I decide, oh, I have to turn it off, it's also very expensive, because on the power grid I have suddenly a huge drop, and in addition it's very expensive to restart a power plant. So I have to be really accurate. Same thing if I'm dealing with an application for, well, a medical application, for example, then the errors are very costly. I can harm the patient. So I have to be very careful. Accepting at 95%, that's not good. Okay. So once we have something that is acceptable, a model that has a good accuracy, then we can now present it with unlabeled data, and it'll label it the way these were labeled by experts. So you have an expert system, basically. Okay. So this framework is used by many paradigms, as I said. There's what we call neural networks, maybe you heard of it. There's k-nearest neighbors, decision trees, Bayesian classifiers, associative classifiers, support vector machines, case-based reasoning, genetic algorithms, rough set theories, and so forth. There are many, many, many ways of doing basically the same thing. So why do we have so many different ways? Well, because there's no winner. There's no method that is better than the others. It depends upon the application. So if I take the spam detector, for example, I have to try them all and see which one gives me the best accuracy. Typically for text, you have support vector machines and Bayesian classifiers that are very good. But if I'm dealing now with other kinds of applications, like, for example, detecting whether this transaction is fraudulent or not fraudulent, apparently neural networks do a better job. So it depends which application you're dealing with, the different paradigms that will perform better than the others. And that's why they all coexist. Okay, so I will not go over the neural networks because I don't have time, but I'll talk very quickly about nearest neighbors and decision trees. So I'll skip the neural networks for the sake of time. So nearest neighbors is actually what we call a lazy learning technique. The system actually will not learn anything. It'll fake it. Like many AI programs, they're not actually as intelligent as us. They're exhibiting intelligence. It's like faking it. It's not really the human inside that box, like in the Turk in 1769. We don't have a human hiding inside Deep Blue. It's really cables and silicon. But it's not really how we don't know actually how we think. That's the truth. We don't know how our brain functions. But let's go back to the nearest neighbor. So the nearest neighbor idea, it's amazingly simple. It uses analogy. So I'm not going to learn anything, but I want to have a new object coming in. I will compare it to the data that was provided to me that is labeled. So imagine I am doing spam detector with lazy learning, with nearest neighbor. Basically, somebody gave me different emails and told me this is spam, this is non-spam, this is spam, this is spam, this is non-spam, and so forth. I'll leave it aside. Each time I have a new email, I'll take it and compare it to all those emails that were provided to me. And the closest one to that new email, I take its label and attach it to this new object. Okay? So I will use analogy basically to label data. Now we have different measures of similarity. I said I take this email and I check which one is the closest to it. There's this notion of similarity, and that depends upon different applications. It's not exactly the same text, but am I having the same words, and so forth. So graphically, basically, this is how it happens. I have, now this is the training data that is provided to me, and the labels are represented here by the color of these objects. I have a new entry. I put it red, means I don't know what label it should be. So I have this program that will check among these which one is the closest. And I see, given some distance function, similarity function. And I'll see this guy is the closest, then I will give this new entry the same label as the closest neighbor. So that's why we call it the nearest neighbor. There's a neighborhood. So if I put this guy among these guys, I'll check in the neighborhood which one is the closest. So this is the nearest, the simplest nearest neighbor approach. I use just one neighbor. There's a possibility of looking at k nearest neighbors, not just one, but a set, a determined set of neighbors. So again, I have this training data. Well, I'm not doing any training again. I'm lazy. So I keep them aside. They're all labeled. When I have a new entry, I'll get the k elements that are the closest to it, given some distance function. And then from this k, I'll do a vote. So I'll see that I have 3 that are gray, for example, and 2 that are green. Well, this one is more likely to be gray. Boom. That's how I label it. So this is very lazy. It seems very simplistic, but it works better than other methods in many applications. Here's another approach, completely different. So in medicine, we use decision trees. It's very common. Well, decision trees are also used as a learning model for machine learning. Here's an example that I took from the paper of Quinlan. Quinlan is the one who presented this idea in 1983. So he said, here's some data representing when a person will play tennis. So this is the history when this guy decided to play tennis and not play tennis. And the data that I have talks about the weather. So whether it's windy, was it humid or not, what's the temperature, high or low, and what's the outlook, was it sunny, overcast or not. And so I look at the past, and I look at how the person decided to play tennis or not. And now I want to build a system that automatically will predict given some conditions of the weather outside, whether this person will play tennis or not. So how do we learn that? We build a decision tree of this sort. So if, for example, the outlook is sunny, then we don't know. Then we'll check if the outlook is sunny and the humidity is high, then we know that this guy will not play. If the outlook is overcast, automatically this person will play regardless of the other conditions, and so forth. So we build a decision tree like that. The question is, there's no one decision tree for this data. There are many possible decision trees. Some are better than others. And the other question is, how do we create this decision tree automatically? Okay. It's easy here. I gave you this decision tree that represents this data, but how do I create it? And there's an algorithm to build it, and that's what the learning is all about. How to learn that model automatically given some data. So there is a process. It's a recursive process. So basically you take all this data, you put it together in the roots. This is a tree. In computer science, the trees are upside down. You have the roots on the top and the leaves in the bottom. It's unusual, but that's how it is. So you start with the top, which is the root, and you put all the data in there, and you say, are they all from the same label? If in a particular node they're in the same label, then you label that node with that class. If not, then you say, how can I separate them? So you have to look at which question should I ask about the attributes of the data in order to split the data into different groups. Okay, so you choose an attribute, and once you select that attribute, you take all the possible values of that attribute. It creates the different groups that have that value for that attribute. And you do it again recursively. You say all this set sample of data, do they have the same label? If they have the same label, then you label that group with that label. Otherwise, you find another attribute to split it, and you continue to do that. Now, there are different techniques to identify which attribute to select. And one example is to see what is the information gain for that attribute in that set. I won't go into details. This is just to tell you that basically there are methods to go over the data and build automatically this decision tree. And in this case, the knowledge that I represent, I don't keep all this data anymore. The knowledge that I keep, that I represented as a cloud before, is this decision tree. Okay? I'm almost done. I want to go through some examples that use machine learning that are specific to medicine, since most of you are in medicine. So here's an example of an application that I'm involved in where we're trying to detect breast cancer in mammograms. So mammograms that are labeled and identify where the cancer is identified, and some mammograms that are normal are provided to a program, and the program goes through all these and creates a model that detects where cancer is, the benign, malignant, and normal cases. This will not replace a radiologist, but can be built in a system that will help a radiologist do his or her job faster. So in case, so rather than, as I said, replacing the human, it'll present the mammogram, and then after the radiologist is selecting things, it can tell it, oh, you forgot this, for example, can you check this area, because there's a high likelihood that there is something in it, for example. Or where it can be used is the case of second readings. So it's recommended that the mammogram be read by at least 2 specialists, because humans also make a lot of mistakes in these. So to reduce the error rate, we have 2 readings. But the reality is we don't have enough readers. We don't have enough radiologists. So here in Alberta, for example, 10% of the mammograms are selected randomly to be sent for second reading. So why select them randomly? You can give all these mammograms to a program that will detect cancer in them, and then the cases where it detects the cancer but with low confidence, it means those are difficult cases. So select those cases to send to a second reader, a human reader, okay? And those where the program was able to detect it with high confidence, it means that the first reader will also detect it easily. Okay. I don't know if it makes sense to you guys. Okay. So again, the machine learning here is not meant to replace humans, but it's meant to help humans in their work, because the final say, for different reasons, it has to go to the human. So here's another case where we use machine learning. So in the case of breast cancer, when something has been detected and we do a biopsy, whether it's from the mammogram or after the doctor realized that there is something, we do a biopsy. And we want to know if the patient is, or basically the cancer is estrogen receptive or not, ER plus or ER minus, because of the treatment will be given tamoxifen or whatever, I forgot the name, you may probably know it better than me. So should we do hormone therapy or should we do other kind of therapies? So ER plus, we will do this hormone therapy. There are many, the pathologists know how we detect this with dyeing, and there's a dye that you put on the thing and you count basically the cells. But here's another technique that takes these cells, we do a DNA macroarray data analysis, and we provide it to the classifier, and we give different patients with ER plus and different patients with ER minus, and the classifier will learn from the data extracted from the macroarray to label this one as ER plus or ER minus. And it happens that this is actually way more accurate than the techniques used today with dyeing the cells. So this technique using macroarray data analysis is also used for SNPs, single nucleotide polymorphisms, and there are many, many applications. For example, detecting learning from previous data whether a patient will relapse after a certain time, whether this patient will reject this transplant or this one will reject it less. So you may provide tools to the doctors to choose which more effectively choose which patient actually should get this particular transplant because this person will reject it, for example. Also, prostate cancer. You can learn from past history to predict whether this patient who has prostate cancer, what kind of toxicity level they will have from radiotherapy. And if you detect that it'll be a high toxicity level, then you will, before doing this treatment, you will prescribe a different treatment, chemotherapy or surgery or something like that. So you have personalized medicine thanks to machine learning. Anyways, there are many, many applications where machine learning now is used. And it's currently used. Some of it is still at the research level, but in some cases it is used. I'll stop here to give you the chance to ask me questions. Thank you for your attention.
Hi.
Hi.
I have actually had some experience with basically trying to improve cardiac diagnostic imaging. And one of the obstacles that we've sort of come across is that we wrote an algorithm in order to try and fuse images together.
Fuse images?
Fuse them together in order to improve their image quality, signal to noise ratio, those sorts of things. And the problem I think that we've encountered is that what we see in the image is not what the machine sees in the image. And this, after a long time, we've started to sort of, I think, come to this conclusion. Well, some of us are still going at it, but my impression is that we're just not interpreting what the computer sees, and so we're having difficulty understanding where the problem lies. And I was wondering whether you sort of had any comments on that, or whether you think that it'll sort of get to the point where the computer will have to do the learning for us,
yeah.
And because we just can't appreciate the information they're seeing. Because if we look at an image, we're looking at the anatomical structures, the pathological defects, the
Yes.
problems with that image, what's right and what's wrong. But the computer doesn't see that. The computer sees amplitude, intensity, signal intensity, pixel density, gray level.
Yes.
Yeah, so I was wondering if you had any comments on that.
Well, I agree with you. And that's why I was saying that actually computers are simulating what we're doing, but the simulation is not how we do it, but they exhibit the kind of output we have. But the way they do it is completely different indeed. So the example with mammography, the features that the program was extracting to detect whether this is cancer or non-cancer are not features that radiologists will use at all. We were using, for example, averages of the gray level of the different pixels. I mean, a human being will not do that. We're measuring kurtosis, for example, to simulate these peaks for the microcalcifications, these dots. And it's not how humans would do either. But it's very difficult to also take what the humans do and try to feed it in the computer, because many humans actually cannot express in a clear way what they actually do. When you ask different radiologists how actually they detected that this is cancer or non-cancer, they'll have different answers. They can reach the same conclusion, but the process of doing it, they learn different ways. So I take another example. I'm working right now, I'm starting this project with people looking at wildlife, monitoring wildlife. So for example, if a company is building a pipeline, they want to show that they don't have a huge impact on the environment, so there's an environment assessment impact on the environment assessed by some experts. And one of the things they want to do is they want to see how many animals are still going there. Is it blocking the migration of animals, for example? So one thing they do is they have these cameras. A camera attached to the trunk of a tree, and it's a motion activated, so when an animal passes in front of it, boom, it takes a picture. So now we have millions of these pictures, and humans are looking at these pictures and they say deer, wolf, deer, bear. They're counting them. It takes a lot of time. So the person that we're working with, he said few people spend the whole summer, last summer, to label about 500,000 pictures. It's not sustainable. So now we're thinking about, we're starting this project, identifying automatically what kind of animal is passing. So we got some images that have been already labeled, these 500,000 pictures, by the humans, and we're feeding it to the computer and say, okay, learn. What is a deer, what is a bear, what is a wolf, and so forth. Well, it's not trivial, because the humans can also, in this case, cannot really tell us exactly how they do it. And to make things even more complicated, it can be at night, it can be after snowfall, it can be in the summer. The picture is completely different, the background is completely different, but also the animal can be facing this way or facing that way. The animal can be very close or far away. In addition, actually the animal can face the camera itself. And if you teach it how to recognize, for example, a deer, and then now suddenly the animal is facing you, the human can do it. Yeah, it's a deer. The human can even say, well, it's a male or female. But we cannot take that description and put it in the computer. So the computer will have to find other features. What are the features that discriminate between a deer that is facing this way or that way or that way? So orientation invariant, or it has to be agnostic from the, even when the deer is looking at the camera. Take other features that humans don't necessarily think about or use and discriminate between these animals. Should we teach the humans to better understand how the computers are doing that, or vice versa? I don't know. We've been trying for many years, and actually the way we're doing it, I believe, is the right way. Because there are features that we humans cannot detect, we don't even look at in the picture, but they're actually very significant and more effective and faster, more efficient to extract and use as a discriminator. I don't know if I'm answering your question, but
I also have one more question.
Yeah, sure.
It was just on a comment that you made about automatically making diagnosis based on ECG. It was a small part of your slide. That has a lot of problems clinically.
Yeah.
I've been frustrated.
This is for arrhythmia, for example.
Yeah,
in the heart.
exactly.
Yeah.
I mean, it creates a lot of frustrations clinically. And I think one of the reasons for that is context, because the context is a very important part of, of whether a small blip on the ECG is diagnostic or non-diagnostic.
Yeah.
And so I was just wondering whether you thought because context is probably an ever-changing thing as well. We probably could never define context completely because every context seems slightly different.
Yeah.
And so is this something that computers will be able to understand, will be able to get good at this, or is this something that will be in...
No, you can teach in the learning, you can also teach about the different contexts, and then you have to provide that context.
But
or,
there's a lot of, I mean, medically there's a
I
lot
agree.
of information.
Or what you do is you say, well, the diagnostic is not completely done by the computer. The computer is only narrowing down the search space. So basically it's a support system for the human who will make the diagnostic, but it'll just raising attention, drawing the attention to some unusual place, basically. Rather than doing the whole diagnostic, it saves time to the human to focus only in the areas where attention is needed. You see what I mean?
Yep.
So it's not replacing the human. Actually, we do not want to replace human in the medical applications.
Okay.
And I don't think we will ever replace the human for legal reasons, because the human has that responsibility. The machine we're not going to sue the machine.
True. Thank you.
We are talking about the car that could drive by itself. Yeah, is there any certain limit for information that you give to the car or not? Or you can give unlimited information to the car? And if you give lots of information to this artificial intelligence or software, it could be confused like human beings, or there's some limitations for it? Just a general question.
There's obviously a finite, there's a limit.
Yeah.
But that limit is way above what we can handle as data coming in. The car is looking at the front, the sides, the back at the same time,
yeah,
and getting all sorts of information, things moving, pressures, all sorts of things. So we talk about a fire hose flow of data coming in, and the computer can handle it. And tomorrow's computer can definitely handle even more. They're way faster. Now, can it get confused? Yes. If I see a sofa on the highway, I'm the car now, I'm confused because I don't know what to do in this case. For me, it's an obstacle, boom, I brake. Now, the human, in this particular case, took over, because the human is sitting behind the wheel, not touching the wheel, but seeing the sofa, that human realized, oh, it's a sofa, the car is braking. He took over and did this maneuver to avoid it.
Yeah.
But what happens is that now the car is learning about this case. Yeah. And if you have enough of those cases,
so it could learn. Yeah.
The car will adapt and will not get confused next time.
Yeah, okay.
Yeah.
Okay. Thank you.
Other questions?
In terms of gene expression analysis, I just wanted to add something. Like, we can also recover the gene regulatory networks from that microarray data.
Yes.
From which we can find out the genes affecting, how they are affecting each
Yes.
other. So that's also one application I just wanted.
Yeah, definitely. So actually machine learning, in the case that I just described, they discovered during this machine learning, not the machine that discovered, but the humans using machine learning doing this research, they realized what are the genes that are really determinant in labeling this ER positive or ER negative, and they are writing a paper to patent it. So the process of using machine learning also helped humans learn something about ourselves.
Question?
We are forcing you.
Yeah, I'll fill time. So my question is kind of more, excuse me, more about the immediate future. Do you see things like companies like Google opening up API access to something like an expert system? So you could say, send a photo and ask, is this a deer or a bear or anything like that? Or like when do those become cost effective versus something like the Mechanical Turk where you can, I think that's what it's called, where you can send data to Amazon and they have a human look at it and send something back?
Well, there are already systems that are put online, not by Google but by researchers. We have one here, for example, Proteome Analyst, where it can detect, for example, the function of proteins. It learns from previous proteins their functions, and here's a new protein that we have. Tell me, for example, its location in a cell. So you upload your data, and the system will learn by itself and then tell you for new proteins where is the location in the cell, predict it, predict the function, for example. So these systems exist, not just for proteins, it can be for other things. And not yet for animals, but maybe we'll make it, put it online. There are systems for identifying mushrooms, there are systems for identifying flowers, leaves, whatever, things like that. So they exist. Little by little, they'll cover a large domain of different fields. Now, comparing it with the Mechanical Turk, these are people who are paid, they're humans. They also make mistakes, but if you have a large number, basically you take the general trend, and yeah, they work. They work for things where you don't have an expert and you want to have an answer very quickly. And it's not just for classification. It can be any task you send to the Mechanical Turk. It could be calculating something or giving an opinion or whatever. So to answer your question, in the near future, well, it already exists for many small domains, and it's growing. People are giving away. They're proud to show that they built something and they put it online. It's available. Yeah. What? Otherwise, you can ask me next time. You'll see me next week, probably. So prepare your questions for the next round, because I'll make sure that, well, I'll present it. Well, I'll have different examples, and hopefully it'll stir some discussion.
Yeah, I think AI is really central to this course. So the fourth and final lecture is a good time for you to sort of tie everything up, so you can be preparing your questions for that. In between now and then, we have Earl Waugh talking on this Thursday about evil as a treatable disease. And then we have Michael Woodside giving two lectures on nanotech. And then we have Dr. Zaiane back. So that's the plan for the immediate future. Okay, thank you very much.